Hello ladies and gentlemen, and welcome to Mr. Saucedo's chemistry class. We're going to be talking about the modern history of the atom today, so make sure that you follow along with your notes so that you fill in everything as you see. So we have to talk about the most famous scientist of the 20th century, Mr. Albert Einstein. And so Einstein used the equation E equals h times v, the energy of light equation, which we spent a lot of time talking about, to show that light can act like a particle. Up to that point, scientists had been sort of curious about how light behaves, and most scientists agreed that light is a wave. In fact, if you would recall back to our equations, all of them involved waves. But Einstein wanted to show that light can act like a particle, not just a wave. Now, how exactly do you prove that? So Einstein decided to perform an experiment where he was going to be shooting particles of light, and we still call them photons today, but he's the one who kind of used the term first, at different metals to remove electrons from these metals. So you can kind of picture it like this. I'm going to try to draw it. So you have a metal, and then you have different, sort of frequencies of light, and he was shooting this light at a metal, and occasionally little electrons would get shot off of the metal. And what he realized while he was repeating his experiment over and over and over again, only photons with enough energy were able to remove the electrons from the metal. So you couldn't just shine red light on a particular metal, let's say, and get electrons to go. You had to have something with a little bit more oomph, a little bit more energy. And so if you had something like, let's say, purple or violet light, electrons would get shot off. Not only that, though, he also, being Einstein, decided to switch out the metals, so he used different elements, and he got the same results with these different elements. So his discovery is actually called the photoelectric effect. Photo coming from photon, light, electric because of the electrons that were being jettisoned from the metal. And in fact, he actually won his Nobel Prize for discovering this photoelectric effect. Now, what made this unique was that the only way you could really sufficiently explain the photoelectric effect was if light was acting like a physical particle, not just a wave. And so this experiment intrigued a scientist called Niels Bohr, who was also around the same time as Einstein. FYI, they did not get along very well. They kind of were polar opposites when it came to physics and chemistry. But that's sort of Einstein's contribution to the modern history of the atom. But notice it used E equals h times v, so the same equation we talked about in class. Our second scientist is named Niels Bohr, and so he was also around in the early 1900s. And what Bohr was interested in, notice the same exact equation, E equals h times v. It's showing up again for a second time. So what he was trying to show was that electrons only orbit the nucleus with a certain amount of energy. So remember, we still have Rutherford's model of the atom at this point, and so Niels Bohr wanted to come up with sort of a modification of that. And so he thought that, let's say this is our nucleus of the atom, and we now know that it's made up of, sort of different particles all kind of stuck together, protons and neutrons. He wanted to show that electrons could only orbit in with particular amounts of energy. So let's say that was our first level, and that's exactly sort of the amount of energy that our first electron or second electron might have. But there was a whole other ring around the outside that would also have sort of a higher energy, and there might be some electrons there. And there might even be sort of a third ring around the outside. And so that was Bohr's idea. So in Bohr's model of the atom, we have electrons that are orbiting just like planets would around the sun. And he needed a term to describe this amount of energy that electrons are allowed to have. And he used the term quanta. This is where we kind of get the word quantity. So think, it just really means like a small amount of energy. So every electron needs a small amount of energy in order to orbit the nucleus. These electrons, like I just said, were just like planets orbiting the sun, but instead of gravity, it was charge that was attracting them to the nucleus. And again, this is Bohr's model of the atom. And in case you're wondering, yes, he did win a Nobel Prize for his interpretation of the atom. So why was his model of the atom at all important? Well, he actually was able to explain a phenomenon which is called emission spectra, something which had troubled scientists for a very long time and something that we really couldn't explain. Well, his model of the atom perfectly explains emission spectra. So here's the phenomenon of what an emission spectra is. You see, when you heat up a gas, it starts to glow. So for neon, we get that sort of orange color. For nitrogen, we get this sort of bluish violet. And then for hydrogen, in this situation, in this picture, it kind of looks a little bit pink. And so that's something that everybody can just see with their own eyes. But what happens when you filter that light? So when you filter that light, you actually don't see those same colors. You actually see something a little bit different. When you filter that light, you get what we call an emission spectra. And so here are two examples. We have hydrogen's emission spectra and we have helium's emission spectra. So remember what hydrogen looked like when it was glowing. Well, when you filter it, you actually get these lines. And those lines are corresponding to a very particular wavelength and frequency. And each one of these has a very unique wavelength and frequency. And the thing about this sort of connection between wavelength and frequency is that these never change. They're like a fingerprint for an atom. So every element on the periodic table has its own unique emission spectra, and no one could explain why. Bohr was able to do that, and he used the very useful equation that we got to talk about, E equals h times v. And so what he realized was electrons can only release energy with particular frequencies. How can you calculate those frequencies? E equals h times v. And so that v right there is the frequency of light that you get. And that frequency corresponds to, well, if I can try to draw it again, those different colors that you sort of saw with hydrogen and helium and other elements. And so his model of the atom, which I kind of show down here, this is his model of the atom, it perfectly explains the emission spectra for hydrogen. And so you can kind of do a very simple calculation, plug it into E equals h times v, and you get, the exact colors and lines that you see in the hydrogen atom. So Bohr's model was very successful for hydrogen. And the reason why I said for hydrogen is because it only works for the hydrogen atom. And this kind of got Bohr mad because he tried to extend his model of the atom to other things, but it only works for hydrogen. So poor Bohr, it only works for the most basic of the elements on the periodic table. So how exactly do we get to this modern idea of what an atom is? Well, our next scientist is called Erwin Schrodinger. Very famous scientist, more famous for his cat actually than anything else, but Schrodinger came up with mathematical equations that described electrons in atoms, and he was very, very successful in his calculations. In fact, from his calculations, he actually realized that electrons can go almost anywhere in an atom. So Bohr and Rutherford, up to that point, we kind of thought of, sort of this would be our nucleus, and then we have these nice little symmetrical circular orbits going around the outside where we have our electrons and stuff. Okay, and so that's kind of what we thought our atom looked like. What Schrodinger realized is that actually that's not the way electrons move. Electrons can go anywhere. They're not really bound to going in a circle or anything like that. So if this is an electron, it could go here, or 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 it could come through the screen or away from the screen. It can kind of move wherever it wants. And that was a big change to thinking about how atoms work and how electrons work. So what he said is it's merely a probability that you can find an electron in a certain location. So rather than knowing that it's moving in a circle or something, we just have probability. And so he really was heavy-handed with the math here. And he used probability curves to figure out how electrons move and how they behave. And his probability curves perfectly describe electron behavior, and not just for hydrogen, but for other elements as well. And so he was way more successful than Bohr was, and yes, he won his Nobel Prize for this. So instead of describing things as being in these symmetrical orbits, he described these probability curves as orbitals. And that's a big difference. I know it doesn't sound like a big difference, but it is. And he said these orbitals give you a 95% chance of finding your electron. Why not 100%? Well, remember, we're basing this all off of probability. And so in probability, 100% certainty isn't exact. I know that seems strange, but there's always a chance that, an electron might be in a different location. And so 95% is about as good as you can get statistically. And so why was Bohr's model wrong? Well, it was wrong because he assumed that orbitals were circular. And so what we find out is, using Schrodinger's equations here, you actually end up with very different looking orbitals. And so this is the simplest, and it is very circular. It's a perfect sort of sphere. And so that kind of explains why Bohr's model of the atom was able to work for the simplest atom, hydrogen. But you also have these other sort of weird, crazy looking shapes. And so electrons can move anywhere in these shapes. And so these are my sort of probability dots of where electrons can move. So they can move anywhere in that little area that you're kind of seeing here. And again, they can move anywhere in that area. In that area, yes, even in this weird sort of donut looking one in the middle here, you'll find a 95% chance of finding your electron in these locations. And so that's what Schrodinger is sort of known for, and that's why he sort of led us down this new road for what an atom might look like. So this is actually our modern idea of what an atom looks like. It doesn't look like what you probably thought, does it? And it's called the quantum mechanical model. We took the word quanta and we changed it to quantum. Why mechanical? Because, well, it is still a physical entity, and so we have the quantum mechanical model of the atom. Now, what the heck are we looking at? Well, I want you to label this, please. So we still have our nucleus in the middle. That hasn't changed. Now, what about all these little dots? Well, each dot that you're seeing here is actually a probability that you'll find an electron in this location. The darker the shade of red, the more likely you are to find an electron there. And notice it gets a little bit less dense and a little bit less red as you get towards that dotted line. What is this? Well, these here, okay, are kind of what we call an electron cloud. It's just a probability of being able to find an electron in a particular location. That's all we can really know. It's probability, so we're not 100% certain. Now, what is this weird dotted barrier? Well, that's what we would call the orbital. And so the orbital itself is where we have, and I'm going to write this down, so you should probably write this down too. That's where you have a 95% chance of finding your electron. Now, that doesn't mean that if we didn't sort of have, sort of a more complete picture, there wouldn't be a dot on the outside. That would be like your 5% chance that you'll find an electron outside of this orbital. But that's the modern idea of the atom. So instead of sort of this, sort of planetary model or something like that, like Rutherford had or Bohr had, we have this very abstract looking model. But it perfectly describes, or almost perfectly describes, the way atoms behave. And so that's our modern idea of what an atom is. So that concludes our lecture on the history of the atom. And so if you have any particular questions, make sure you ask tomorrow, but we're going to be looking at these scientists in a little bit more detail.